this video, we'll be looking at the first part of the particle physics and quantum phenomena topic, atomic structure. When considering atomic structure, we are generally referring to the basic knowledge that you start with from GCSE, and we will gradually build that up throughout the entirety of this topic. Now, protons, neutrons, and electrons are the three parts of the atom that you are well aware of. The protons and neutrons located in the nucleus, whilst the electrons much smaller and in orbit. Now we can see some basic ideas here, like the fact that electrons are smaller, the nucleus is clumped together, really tightly packed, and that the electrons are in different orbitals, different shells. Now at this level, we have to actually start considering real values, no longer just dealing with relative charge and relative mass. Now they serve their purpose at GCSE, just for comparison and understanding the general structure. But at this point, we need to actually carry out calculations and therefore need actual values. So +1 and -1 for the relative charges protons and electrons, and 0 charge for the neutron, whilst the relative masses of protons and neutrons are the same as 1, and the electron has a much lower mass, 1/2000, or whatever variant of that suggests it's negligible. Now we need a charge in coulombs and a mass in kilogram. Now they are your standard units. So when we consider the charge, your data booklet provides a value for the magnitude of the charge of an electron, which is 1.6 times 10 to the minus 19 coulombs. Now we know it's negative for the electron, so we add the minus symbol, whereas the positive of this same value will be the charge for the proton. So they are still the same in that relative sense. Just be wary, because they do give you as a magnitude. Don't assume that suddenly an electron's positive. Now neutrons obviously still have a charge of 0. Nothing has changed there. Now when we consider masses, the mass of an electron is absolutely tiny. 9.11 times 10 to the minus 31 kilograms. Now the masses of the neutrons and proton should be very similar to each other, but are not exact. So both have a mass of 1.67 times 10 to the minus 27 kilograms. However, a third decimal value of 3 for the proton and 5 for the neutron are also provided. This is to show there is a distinct difference, which is relevant for decays later on, but you never need to use those bracketed values. So the bracketed values can be ignored. So all nucleons, all things that reside in the nucleus, are treated the same. Now specific charge is a new quantity, and as we can see, it is measured in coulombs per kilogram. So that tells us we're going to take a charge value and divide it by the mass value. Now for these three parts of the atom, the basic quantities you need to know, you are given the specific charge for each of these on your datasheet, and it is listed as charge/mass ratio. Now the obvious one to get out of the way is the neutron. 0 divided by anything will still be 0. So the specific charge of the neutron is naturally going to be 0. This isn't listed on the datasheet, but it doesn't really need to be. The other two show a distinct difference. in how the charge relates to the mass. So for a proton, 9.58 times 10 to the 7 gives us a value to compare most nucleus values for specific charge. So 10 to the 7 is where you would expect any nucleus to have a specific charge of. Now, the electron has 1.76 times 10 to the 11, which is significantly higher and demonstrates its mass being much smaller for an equivalent charge. Standard notation will still be used to represent key features of an atom. So X is your standard symbol, and that will be given to you in all circumstances. There is no expectation that you know the periodic table, and you will not be given one to seek these out. So instead, you will always be given the symbol you need to work with. Now, A and Z both have key meanings and key definitions that you need to be specific about. A represents our atomic mass number, whereas Z represents our atomic number. Now, mass is always larger, so should always be top, with a smaller number below as Z. But you need to remember the reason for this. The atomic number defines the element, and it is the number of protons present, not electrons, protons. Whereas the mass is the total mass of the nucleus itself. So that is the total number of protons and the total number of neutrons present. So if we were to consider a basic element like carbon, carbon will have 12 nuclei and 6 of which are protons, which tells us that 6 of them are also neutrons. But we could have a different variant of carbon. We could have carbon 14, which would have a mass number of 14, indicating that it actually has 8 neutrons instead. Now this is an isotope. Now you've covered isotopes at GCSE as well, and it still carries the same basic definition. So knowing that there's a different number of neutrons is the key feature. However, in order to guarantee that you get the marks every single time, you need to make sure you state that they have the same number of protons and the different number of neutrons. Both of those statements being present can award you 2 marks. Even at A level, this is awarded 2 marks. So very easy and very worthwhile. So if we consider these 3 examples here, these 3 isotopes of hydrogen, they are easy to illustrate using the standard notation. Their symbol for hydrogen, pretty unsurprisingly, is H. The atomic number, so the number of protons, is 1, and there is only one thing in the nucleus, so 1 on the top. And the other 2 should have the same symbol, because they're still hydrogen, and the same bottom number, because they are still hydrogen. Proton number defines the element. The top number will vary pending the number of nucleons, hence 2 and 3. So staying the same, number of protons, changing number of neutrons. Both must always be stated. Now, considering specific charge itself, you are not given an equation for this in your data booklet, but it's fairly obvious. As they give you values for the specific charge, the charge to mass ratio for both the electron and the proton, the unit for each is a reminder that specific charge is just a ratio of charge and mass, that you're dividing charge by mass. Now be aware, in questions they can and will alternate between referring to this as charge to mass ratio and specific charge. They are the same thing, so it doesn't matter which one you write, they will try to catch you out by varying it. So all we're doing is dividing the total charge present by the total mass. Now that means this will never come up for an atom, because any atom will have the same number of protons and electrons, meaning the charges would cancel out, so the specific charge of a normal neutral atom will be 0. So instead, it'll be a nucleus or an ion. So let's look at an example of this. So in this example, we're going to find the specific charge of a nucleus. So we're ignoring all electrons. And we're going to look at the nucleus we referred to earlier, carbon-14. So carbon-14, being carbon, has 6 as its atomic number and 14 as its mass number. Now taking our key values from the datasheet, we know that the charge of a proton is 1.6 times 10 to the minus 19 coulombs. Charge of a neutron, 0 coulombs. The mass of the proton and the mass of a neutron are both 1.67 times 10 to the minus 27 kilograms. Which means we can actually lump together all of the nucleons. So everything in the nucleus, in terms of mass, can be clumped together. So all we have to do is apply the equation. Now we know that the total number of charged particles that we actually have present is going to be 6. So our amount of charge on the top will be 6 multiplied by the charge of a proton, which is 1.6 times 10 to the minus 19. And as we are disregarding the bracketed values from the data booklet and taking the mass of a proton and neutron to be the same, the bottom is simply the number of nucleons, so 14, multiplied by the mass, 1.67 times 10 to the minus 27. And plugging that through a calculator should give you a value that is quite long. So we end up with a value of 4106355.67. And that's not going to be our final answer. We want 3 significant figures. Every final answer should be nice and crisp. 3 significant figures, standard form. So this will give us 4.11 times 10 to the 7 coulombs per kilogram. Very often, they will award a mark for the unit for this one in particular. And as we said earlier, 10 to the 7, the range we expect for a nucleus. Thank you for your time.